All right, my name is Sam.
And I'm Mateo.
And this is our demonstration of the SOS 2.0 project entry into the NASA Minds competition. We basically are designing a software framework to use with a Raspberry Pi computer inside of a handheld box, essentially, that would let us detect damaged structures outside of the Earth. We do this through a couple ways. Firstly, through detecting temperature, through detecting distance, and with an AI model that we can use to detect cracks in an image. We wanted to add more things such as vibration detection and accurate range finding, but we were unable to do so with the time we had.
This is a demonstration of the non-functional model of SOS 2.0 by the Georgia Gwinnett College team Grizzly Bears, which will cover our intended design and layout of our hardware and the chassis using our first chassis model. Today I will not go into the details regarding this prototype's software because we will explain it in depth in our software video demonstration. We will begin with the exterior of our model. The handles are orientated horizontally for ease while you're carrying the prototype. The space in between the handles and the body allows for contactless utilization via a robot, such as with a rover, to pick up and transport the device to analyze environmental and surface conditions. We also have a 5-inch monitor to provide a visual representation of our collected sensor data. On the top of the chassis, we have a cover to secure the batteries because they are not packaged with fasteners such as screws or nails. For our model, we have 2 hardware pieces in place of the solar-powered batteries. The solar-powered batteries are intended to collect energy and transfer them directly to the Raspberry Pi to provide it with power. On the interior side of our model, we have our distance sensor. This sensor determines how much space is between the prototype and objects in front of it, which provides the user with an estimate of where the prototype is in relation to the structures around it. We also have our temperature sensor. Our temperature sensor determines the thermal energy surrounding the prototype. We also have our HD camera, which provides the user with a view of the prototype's surrounding environment. In the interior of our model, we have several hardware devices. The NVIDIA Jetson Nano is an alternative to the Raspberry Pi 4, for demonstration purposes only. The Raspberry Pi is our prototype's motherboard and CPU. The Pi will also control all of our system processes and run our software. In the model, we also handle connections between peripherals. The connections for these pieces will run through the left and the right faces because they're hollow and they allow for clean and organized wire connections. The distance and the temperature sensors only have a pin connection, so we use DuPont wires, otherwise known as jumper cables, to connect these sensors to our breadboard, which will then connect to the pins on our Raspberry Pi 4. Those pins are very similar to that of the Jetson Nano, which we are using for model demonstration purposes only. On the bottom of the chassis, we have several holes. These holes are to allow for airflow and ventilation, primarily from our Raspberry Pi 4.
Okay, so I'm going to talk to you about some of the components in our dash. All the components you see here are updated in real time without the need to refresh the page. This is exceptionally useful in our use case because we're able to run our camera temperature and distance scripts in the background, and all this data will be able to be updated in real time and reflect that. So these graphs will be plotted according to our real-time data. In the dashboard, I also incorporated a feature for crack detection. This is an artificial intelligence feature, and it works by using image segmentation technique. Some of the steps in this technique are to use edge detection, meaning gradient vectors are calculated for each pixel, And after that, we use a non-maximum suppression to thin edges and obtain a 1 pixel edge. This was an existing model I found that I have modified for our particular use case. I want to show you a brief demonstration. Here's a picture of a crack, and you see all the cracks and edges are able to be detected. No crack here, so no crack detected. Crack here, crack detected. Crack here, so the crack will be able to be detected. My phone screen a little bit closer. Of course, this will run better in person rather than the webcam looking at a phone screen. The glare kind of messes it up as well. Another picture of the ground just to prove that the crack detection does indeed work. That's what I wanted to show you, and I'm going to show you also how our graphs are updated in real time. So if I update some of the values in our graph, as you see, I updated my temperature and my distance value, and then of course this the graphs updated, and then the elements up here did as well. And that was our demonstration, and I'd like to thank you for giving us this opportunity.